storage media. So we discussed about flip-flop. Then we discussed about SRAM. Then we discussed about SRAM. Then we discussed about SDRAM. Can someone tell me what is the benefits of SDRAM and what are the drawbacks of SDRAM? So what are the benefits? Reduced memory footprint. Basically, amount of memory to store. Let's say we have 2 GB memory in our mobile phone. If I use SRAM, I will require minimum 6 transistors to store each bit. Whereas with SDRAM, I will require only. Yeah. Read this. So in the last session, we discussed about all these benefits and drawbacks of various memories. Then we also discussed various requirements. So then we quickly went over the different features that are supported by memory controller. So then we understood the architecture of memory controller. So today what we'll do is we'll take this memory controller architecture, we'll understand the various components and their functionality. Okay. So can you make a note of various components in memory controller based on whatever we discussed last week? Don't look at the slide. Please make a presentation, note of what all components we had. Okay. So the first component you see in this diagram is wishbone interface. So let's understand what is the functionality of each block. From the architecture itself. This is where processors will be connected. Like this is the interconnect line. Into the interconnect wishbone interface, this will connect. This is where my processors will be sitting. Processor 1, processor 2, processor 3, like that. What they will do, their whole idea of process is what? There is a memories connected here. Write to those memories, read from those memories. But to do that, we can't just blindly do it because there can be various types of memories connected here. One can be SDRAM, one can be flash, one can be SRAM, one can be a synchronous chip select memory. There are various types of memories. So there can be various types of memories. So we can't blindly just start reading memories. Also, it's not that only one memory is connected, right? There are multiple types of memories which are connected. In those cases, there is a need to program the registers here, where you tell what is the type of memory connected here. For example, there are how many chip selects possible? Chip select 0 to 7. What is mean by chip select? It's the point where one memory can be connected. So if there are 8 chip selects, how many memories total you can connect? 8 chip selects. So to tell characteristics of each memory connected, we have registers here. That is called as chip select configuration register 0 to chip select configuration register 7. So what does the chip select configuration register will tell? If you go to the spec, you will understand that. Memory controller. If you go here, if you see one of these registers, chip select configuration register, what that will tell is, there is something called as base address. We'll talk about base address in some time. Basically, base address is used to decide which chip select is being targeted. When I generate one address from the here, when I generate one address here, basically that address is targeting which chip select. To decide that, we'll use this selection line. Sorry. Okay, this selection line will be used for that. Parity enable will tell whether do you want to generate a parity bit or not. Generally, you know, right, parity is generated to do the data integrity checks. When you are sending 8 bits, along with that you will send one more bit, which will keep either even parity or odd parity. Based on that, you check whether the 8 bits are coming properly or not. Then other features like, do you want to keep the row open? Once you have completed writing, reading SDRAM, do you want to keep the row open? That is KRO. Okay. Similarly, okay, yeah. Okay, keep row open will tell that keep the row open. Once you have accessed the memory, there is a concept called as keep row. I mean, when we talk about SDRAM little further, you'll understand that there is this concept of keeping the row open. Whether you want to keep the row open or not, it will tell. Bank address select. Write protect. Do you want to write protect the memory? I mean, is it only read capable? What is the memory size? Did you connect 64 megabit memory or 128 megabit memory? 256 megabit memory. What is the bus width? Whatever you are accessing here, in this case, whatever you are accessing the memory, is it 8-bit width, 16-bit width, or 32-bit width? That is what it will tell. Then memory type will tell what type of memory is connected. Is it to the chip select? Is the SDRAM connected? Is the SRAM connected? Is asynchronous chip select device connected or synchronous chip select device connected? So all that it will tell. The last bit, 0th bit, will tell whether the chip select is enabled or not. If let's say it is not enabled, if it is disabled, even if you connect any memory, whatever configuration to it, won't work because you haven't enabled the chip select itself. Right? I hope it is clear to you. Sometime back we were discussing about this concept of keep row open and all those things. Let's just spend some time and understand what is concept of this keep row open and all those things. So before we go ahead, do you have any questions from last session? Okay. Now specifically one question is why we specifically take memory controller is it's a very good learning project for every fresher. I mean anyone who wants to learn verification concept because it involves multiple aspects. It involves the concept of timing diagrams, working with various types of memories, working with these complex scenarios where you have connected multiple types of memories to the memory controller. So it becomes a very good project. That's the reason we specifically take this one. And now let's start with understanding SDRAM functionality. As you have seen some time back, that SDRAM has a drawback that it is slower in access. But what is the benefit? It's a lower memory footprint. This is the most important factor. Why is it important factor is, in a typical SoC, if you take any mobile phone SoC, 75% of memory chip area will be memory, and most of it will be based on DDR. If I don't use DDR, if DDR is not used, if in place of DDR, if we use let's say SRAM, then it will take, instead of let's say it consumes, let's say 100 square mm square. Instead of that, it will consume 600 mm square to the same to achieve the same functionality. So which will increase my chip size by what? 6 times. If in place of DDR, if we use SRAM, this much area will be used. Hence, we want, basically for us at one point, more than speed, area becomes important, because imagine a chip which is as big as my cell phone. Then my cell phone has to be 2-3 times bigger, right? So cost will increase. There are a lot of other factors associated with it. So idea is, how do we use DDR still improve the speed of access? So that is the question we need to address now. To address that question, what we do is, now we need to understand, take it forward, we need to understand various features that SDRAM supports. What all things SDRAM supports? SDRAM supports, SDRAM is based on capacitor transistor plus one transistor plus one capacitor model. Means the charge, the 1 or 0 is stored in capacitor. How does SDRAM, how does this work? This is the capacitor, ground. There is a transistor. This is called as write line. This is called as bit line. Write line will tell whether you want to perform a write, whether do you want to access the capacitor or not. Bit line will tell what do you want to do, whether you want to write or read. Let's say you want to write 1, what you do is you connect it to VDD. Then what will happen? High voltage. Because of this connection, and you enable the write line, what will happen? Because of that, this charge will go from here to here. So when this goes beyond one level, though it means it is storing 1. Let's say you want to read, what you do is, during reads, during writes, whatever you want, let's say during write, let's say you want to write 0, what you do, you connect it to ground. You remove this VDD, you connect it to ground. What will happen? Charge will come from here. Right? So because this gets discharged, it will become 1 to 0. And you know that anytime you are dealing with capacitor, the transfers will be very slow. The way it will happen is like this. Initially it will be fast, but to reach a stable value, it takes a lot of time here. See, this is the time that we are talking about. This is what is slowing down the whole capacitor based access. right? Let's say when you want to read, what you do is you don't keep it at 0 or VDD, you keep it at VDD by 2. What do we do? VDD by 2. When you connect it, when you enable write line equal to 1, based on whether this charge increases or decreases, you will come to know whether it's 1 or 0. If it, let's say if it increases, means what? There was 0, that it got incremented. That means what? It got, I mean, it incremented means what? Earlier it was less. That means 0 is the 1. Let's say it was 1 means it will get charged. That means 1 is here. So based on that we do. Basically, what you need to understand here is SDRAMs are accessed by SDRAM cell is accessed by sensing the charge on capacitor, and which will be very slow. To solve this problem, what we do is we use something called as sense amplifiers. What sense amplifiers will do? For every, like, let's assume this as a one cell now. I'm just drawing it as a one diagram. Okay, just remember this diagram. What we do is, when I have memory is generally organized into this kind of cells, small cells. Each one is a one cell. Whatever a big block diagram I draw, right? Like this diagram. Instead of accessing this cell directly, this is called as row. Whatever you're seeing, this is called as row. Each element is called as one column. What we do is we parallelly keep something called as sense amplifiers, which are nothing but SRAMs. Which are nothing but what? SRAMs. Anytime you want to access SDRAM, you don't access these cells. What we directly rather do is you copy the content into here. That process is called as activation. You are activating one row. Anytime you want to close the row, I mean, let's say now you want to access another row. So, but I have only one sense amplifier row. I can't keep two row content in the same sense amplifier. I have to close it. That is called as pre-charging, and I have to open that again. So activating. So what are the two terms we discussed here? Activating means copying the contents of SDRAM row into sense amplifiers. So write reads happens where? Write reads happens to sense amplifiers, not to SDRAM row directly. So this ensures that access is faster, because you are not dependent on capacitors anymore. Now, if user wants to access a different address, which is different row or different bank, then existing row must be closed so that new row content can be copied to sense amplifier. This process of closing row contents, that is copying from sense amplifier to row, is called as pre-charge. I think I should have had included this whole thing. I don't know why I didn't do it. SDRAM operations. Activating a row, recharge, refresh, self-refresh, auto-refresh, timing associated with each operation. is write, read, activating, recharging, self-refresh, auto-refresh. With everything, there is a timing associated. We need to understand the timings. What is the need for banks? Need for banks. Okay, yeah. So let's understand one by one. So I hope by now you understand what is meant by activating a row. You don't want to directly deal with user do not want to directly write read to SDRAM rows, because since it will be slower in access, hence row contents are copied to SDRAM sense amplifiers, bank sense amplifiers associated with bank. Precharge means what? Closing this row, closing the current open row, and so that a new row contents can be copied to sense amplifier. What is self-refresh? Why do we need refresh? SDRAM is based on storing 1 or 0 in capacitor, and it is by default prone to discharge, right? So it need to be regularly refreshed. Refresh means if it is one means, otherwise if you don't do anything, what will happen is it keeps losing the charge. At one point it will become 0. So it need to be refreshed, regularly refreshed. That this process is called as refresh. Sometimes memory controller can be put in power down mode, power down or suspend mode, so that power consumption can be minimized. Still, we may want to, user wants to restore the SDRAM contents. So that time, during that time, SDRAM by itself does self-refresh without intervention of memory controller. Whereas in this case, memory controller initiates refresh process, refresh operation. Okay, I hope this is clear to you why we need to refresh. What is refresh? Simple. Capacitor charge being brought to 1 or 0 level every frequent times. I mean, it can't be like once in a day. It will be more like once in a 1 millisecond or once in 10 milliseconds. Once in, I mean, it depends upon memory organization, how memory has been organized. That is where timing comes into picture. Every operation, every memory controller operation requires a time. It can't get over in a 0 time. Let's say I want to go from here to some other place. Does it happen with my thought that I mean, within no time will I reach there? No. So same way, any operation, every operation takes time. So while one operation is in progress, any other operation can't be performed. Can't be performed. For example, if refresh is in progress, okay, if refresh is in progress, write read can't be done, precharge can't be done, activate can't be done. we can't do any operation while one operation is in progress. Let's say write read isn't happening. Same applies to other operations also. But each operation takes time, so there will be a timing that you need to maintain. These timing values, I'll do one thing. Just okay. These timing values are not fixed. What is it? These timing values are not fixed. They are dependent upon type of SDRAM, size, number of banks, a lot of factors, etc. So many factors are there. So for that reason, to configure these values, timing mode selection register will be configured. So now what all values are required? What all values need to be configured? So please refer to individual operation timing diagrams. For example, if I go to this specification, operation, if I go here, if I talk about SDRAM, so there is one timing value, TRCD. What is this? TRCD means once you have issued a activation, once you are activating a row, you have to wait for minimum TRCD amount of time before you can do write read. So what is TRCD? One example I'm telling. TRCD. Once a row activate command is issued. Write read can only be done after TRCD time. Anything you do before that, it will result in a wrong behavior. Like that, for every operation there will be timings. For example, you are pre-charging, means what? Closing a row contents. You have to wait for minimum TRP time. Only then you can do a new row activation, because it is physical, right? You are copying content from sense amplifiers to capacitors to sense amplifiers. It takes time, that calculation. And do you think it will be same for all the SDRAMs? It won't be same. Based on many factors are there, right? So that will decide all these concepts. So like this, if I go with this, there will be many timing parameters. So for example, here you see T write. Once I perform a write, how much time does it minimum take to complete the write? So that you don't do any operation before that. Let's say you did auto refresh. How much time you have to wait till before you can do activation? Like that, for everything there is a time. So putting together all of them, these are the various parameters. This register is called as timing mode selection register. This is called as what? Timing mode selection register. It is on page number 18, right? I hope this is clear to you. Okay. What is the need for banks? Why we need banks is we want to minimize above dependency. Idea is what? I mean, if refresh itself takes complete time, if refresh itself take a lot of time, so we are basically limited. We are limited by available time for write reads. So what we do is to solve this, divide memory into banks. So while one bank is refreshed, other bank can be right read. It is possible. Hence we divide this into various rows. Sorry, various banks. Okay. Need for row and columns. What is the need for row and columns? I just minimize size for time. What is the need for row and columns is generally a row size will be very big. As much as 4096 bytes each row will have, like that. I mean, it can be big, right? The idea is, in general, we will discuss next step called as how addressing works in SDRAM. Addressing works in two stages. First stage, a bank is selected. A bank and a row is selected. So this row content is copied to what? Sense amplifiers. Second stage, a bank and a column is selected. Ideally, bank is not need to be selected, because it is possible that why again bank need to be selected? Question should be, why a bank is again selected? There is a possibility that we may want to access a different bank now. We may want to access different bank. For that reason, it is required. Now, when we select a bank, when a column is selected, we are actually selecting a word data. We are actually reading or writing a word data. Word means what? 32 bits. So this is how it works. Is it clear to you? Now this is where all these concepts come into picture. TRFC, TRP, timing parameters, why we need various core registers, everything. So now let's go back to our slides. I hope this will help you understand what is meant by open bank and row tracking. I mean, it will keep track which bank is currently open, which row is currently open. Based on that, it will decide, should I issue a activate, or should I issue directly write read? Let's say you are continuing to access the same row contents, because each row has how many contents? 4000. I mean, possible that each row may have 4096 bytes. So if we are accessing, right here. So if a row is already opened, if we are accessing continuous address locations, then there is a chance that there is a very high chance that we will be accessing same row. Same row contents. Hence, it will be beneficial not to close the row immediately after accessing the row, because uh, because activating and recharging will take time. We want to, so to support this, to fix this, to ensure that we don't, to make it efficient, we will use KRO feature. Can you read this once? Recharging. So I hope you got the clear idea of how SDRAM works. Now I want you to go through the SDRAM functionality. You will be able to understand these things in more detail. Now let's understand what is significance of this. This is used to keep track of among SDRAM memories. Let's say these two are SDRAM memories among 8 memories. It will keep track which bank is open, which row is open. So if you are accessing again same row, it won't pre-charge and activate again. Let's say you are accessing a different row, it will pre-charge and activate. That whole thing it will do. Let's keep track of why we need refresh controller. Can someone tell me why do we need refresh controller? I think everyone can talk, right? Can someone tell me why we need refresh controller? Or you don't even know what is refresh? So I hope you understood the significance. Basically, it decides when refresh should be issued. Basically, it will calculate a lowest refresh time and accordingly keeps issuing the refresh. And refresh doesn't go to one; it happens to every memory. Power on configuration, we know, right? I mean, yeah. Basically, the point is for everything, this is the input. See, input for everything. Register programming is the input. And finally, all the operations go to whom? Memory timing controller. That will decide what operations to be done. Address is for generating the address. Data is for handling the data write reads. like that. So next, let's go to the next slide. So what all components are there? Can you read this once? Wishbone interface, power on configuration block, refresh controller, open bank and row tracking, address multiplexer and counter, data latch and packer and parity, memory timing controller, memory interface, clocks and configuration register. Can you read what is the need for wishbone interface? Basically, memory interface is the, I think I'll move this slide. Processors will issue register and memory write reads commands to requests. I would say not commands, requests to memory controller through this interface. So wishbone interface will decode this instruction and forward those to appropriate blocks. That is the role of this. So while doing that, there will be various signals are generated. Like wishbone write to go means it indicates a write cycle. Read go means read cycle. Let's say if you are doing a burst cycle, first will tell that it's a first transfer. Wait will tell that there is a wait happen. It's very simple. It's like a interface. This is the wishbone interface through which processor either write reads registers or write reads memories. That's all. Even configure power down controlling everything. Next, what is the role of power on configuration? Latches the value of memory data bus during reset. This value determines the initial configuration of memory control, provides additional configuration. Basically, in simple terms, when system is reset, processor needs data, needs boot information from a memory. So POC register will hold the default location in memories from where processor will get the data from. Get the data from. So this whole thing is taken care by the power on configuration block. Right. Without this block, processor will not know from where to boot up. What is the role of refresh controller? Generate refresh cycles request to SDRAMs. All SDRAMs are refreshed at the same time with shortest refresh interval among all used for the all SDRAMs. Shortest among all SDRAMs. Okay. Refresh request remains asserted until refresh is performed. While refresh is happening, while refresh is in progress, no operation can be done. No other operation can be performed. But however, other banks can be accessed. That is okay. Open bank control tracking. What do you mean by this? Can you read this? It keeps track of which bank and which row in the system are being currently accessed. By keeping the open bank and row tracking numbers, you know that which is the currently being accessed. So you can, so if you are trying to access the same thing, you don't need to again activate it. So to keep track of that, we use what? Open bank and row tracking. This block is used only when KRO, keep row open bit for the chip select is set. What is the role of address mux and counter? I would say generating address for following devices: synchronous chip select device, asynchronous SDRAM device, based on the memory type in the chip select configuration register, CSC register I would call it. The proper address is selected. What is the role of data packer and data latch packer and parity? It's a data bus connection between wishbone bus and the memory bus. Data that goes out to the memory bus is latched at appropriate times. Data read from memory bus is either passed through latch or goes through the data packer first, then to wishbone bus. Basically, when the data goes from wishbone to the memory, through the data latch packer and parity block, it goes. Next, what is memory timing controller? Can you read that once? Generating control signals for the memories based on configuration registers. All these values are present where? In the timing mode selection register. Right? Is it clear to you why we need a memory timing controller? Without that, we don't know when to issue refresh, when to issue activate, and all those things. Then what is the memory interface? It is the provides a synchronization for IOs. IOs means what? Memory pads. All inputs or outputs are registered at the rising edge of memory clock. Then you need to generate two clocks, right? Wishbone clock and memory clock. Memory clock is derived by dividing wishbone clock by 2 and then phase synchronizing it to the wishbone clock. Then what is the need of configuration and status register? It holds all the registers in memory controller, generates a request to update mode register within STRAMs whenever value of TMS register changes. I hope it is clear to you what is the functionality of each block. All this block functionality is there in this description. Everything has been taken as it is from these slides. I mean this spec, everything. Okay. Now let's understand the operation of various blocks. Can you read this chip selects once? Okay. Each chip select can be programmed to choose choose the address space and memory configuration that chip select controls. Please read these remaining things. I'll explain. So when we have connected, let's say 8 chips here, 8 memories here, when a processor is generating address, there is someone who needs to tell which chip is being selected. There is a specific block which will decide which chip is being selected. So based on that, there will be a signal called as at memory interface CS_N 7 down to 0 will be used to decide which chip is being selected. Which chip is being selected? That means if CSN is equal to 8 tick B 11111 1110 means chip select 0 is selected. That means what? Memory, now any write reads will happen to memory connected at chip select 0. It can be any memory. It can be any memory. It can be SDRAM, SRAM, it doesn't matter, etc. Anything. CSN 8 tick B 00111111. Can someone tell me what does it mean? Can someone tell me what does it mean? CS7 and CS6 are selected currently, which is illegal because two chips can't be accessed at same time. That means same address can't correspond to two locations. Hence, this is illegal. So, if it happens, someone should generate error. Okay. As in a single test case, however, in a single test case, multiple chips can be selected, but however, only one at a time, at any time. I hope this is clear to you. Now let's understand how does this chip select logic works. Chip select maths algorithm logic, chip select logic. Simple, it is simple. What we do is there is this register is there. If you go to core registers, each chip select configuration register has a selection line. Chip select n register. What is the fields? 23 down to 1. Okay, there is a pin called as chip select. This is called as selection cell. What it reads is, if you read this, base address this field is ANDed with the address mask. There is a register called as BA mask register is there, which is 8 bits. BA mask ANDed with CSCN 23 down to 16. if it is equal to wishbone address. Wishbone address means what? Processor issued address. 28 down to 21. Then chip select N is selected. And it is not possible that it is illegal to select multiple chip selects using single address. It is not possible. But even if you do some gimmick and do it, it is illegal. So what does it mean? So initially, why this is done? I mean, it is done, above is done to reduce the number of registers. Otherwise, without BA mask and selection, we will require 16 additional registers. Why 16 registers? 2 registers per each chip select. Chip select start address, chip select end address. Like that, 2 into 8 chip selects. So totally it will make 16 registers to store the addresses would be required. But by using BA mask and selection values from chip select configuration register, we are able to avoid 16 additional registers. That's the whole point. I hope it is clear to you. So when an address comes, there is this calculation that happens. Base address mask, chip select this, no, once again, and it with address mask and compare to address input. If there is a match, that this chip select is being accepted. Is this clear to you? Okay. Next is what? Memory organization. SDRAMs can be 64 megabit, 128 megabit, 256 megabit. All SDRAMs connected to the same chip select must be of same type. What does that means? If SDRAM used is a 8-bit SDRAM, means data width is what? 8-bit data width SDRAM. Data bus width DRAM. Then 4 SDRAMs same must be used to ensure that 32-bit is added up. That it ensure that it all adds to 32-bit. 32 bits in total. Same thing. If 16-bit SSRAM is used, then 2 SSRAMs must be connected to same chip select. Understand here, I am talking about to the same chip select, so that both adds to 32 bits. So when a write or read happens, the same location in both memories, both are multiple memories will be accessed, each giving 16 bits or taking 16 bits. So totally adding to 32 bits. But SDRAM asynchronous chip select device is the only exception. Here we will not use multiple memories. Asynchronous chip select device is nothing but a flash memory. Why it's called asynchronous? It is called asynchronous memory because there's no clock involved. There's no clock involved in this in flash memories. We will not use multiple memories. Same memory is accessed multiple times. 8-bit data bit means write read is done 4 times. Same as in synchronous chip select device, it's same as SDRAM, SRAM. In terms of only for memory organization, memory connections. Otherwise, everything else is different. I hope this is clear to you. Do you have any questions here? That means what? Even though one chip select here, 4 such memories will be connected. 1, 2. If it is 8-bit, each is 8-bit means 8, 8, 8 adds to 32 bits. I think already we talked about how SDRAM works overall. So let's talk about SDRAM memory timing configuration. Can you read this once? Memory timing is defined in a register called as TMS register, timing mode selection register. There are 8 such registers because you can have 8 memories connected, 8 chip selects. Each memory type has a different meaning for TMS register. Basically, if you are using SDRAM, it means SDRAM timing register. If you are connected SRAM, means SRAM timing register. SDRAM may operate in 2 modes, keeping the current row open, closing the row after read-write operation, write-read command. Right? So this diagram will show you how this works. Okay. If you see this one, this is the example where row is closed. In this case, once you close the row, let's say already you have closed the row, all you have to do is what? Activate a new row and then perform a write read. That is this diagram. In this case, let's say you don't close the row, what you have to do to access a new row, if you are keeping the row open, what you have to do to access a new row, you have to pre-charge the existing row, close the existing row, activate a new row, then write read. So even though it may look like this is taking more time, it is not. This is the worst, this is the bad performance. Because you still have to do pre-charge. Somewhere you would have done pre-charge. But in this case, the benefit is what? If you are continuing to access the same row, you don't have to go through this pre-charge activate again and again. Right? So please read this. All this information is present in the specification. This diagram as it is taken from the spec. If you go to operation, you will find every diagram there. See, all these diagrams as it is copied from that. All you need is a little patience. Some 4-5 hours of dedicated time. Then you can completely understand everything. Next about SSRAMs. I don't know why I have to say so much space. This talks about SDRAM timing configuration. It talks about how write reads happen. Once you issue a read, there will be something called as CAS latency. After that time only data comes. Even though you should read here, it takes this much time for data to be coming. Let's say now issue something called as burst terminate. What happens is after 2 cycles, termination happens. What is meant by burst terminate? Is actually you can do configuration only for burst length of 146, 148. If you want to do anything other than 148, you have to issue a 148 command, but you have to issue the burst terminate in between, so that you only do 3. In this case, how many bursts are happening? 3. But there is no way to configure 3. What you do, you actually issue 4 bursts, but in between you terminate, so that only 3 will happen. Okay, when do we do that? When transfer is smaller than program bursts, burst terminate is issued. Same thing here. In case of write, burst terminate is immediate. When you issue burst terminate, it terminates immediately. Whereas in read, it takes time. See here. Next. How SDRAM auto refresh works? Can you read this once? Okay. Memory controller generates auto refresh cycles. The frequency of auto refresh counter is determined by TRFC field in the TMS register. So the minimum value among all the registers is used. I mean, among all registers, among all TMS registers corresponding to SDRAMs, minimum lowest TRFC is used. Okay. So that is the TRFC here. How does this numbers work basically? This shows the sample calculation. If you see this calculation, you will see that in SDRAM mode, write to TMS register initiates the write to SDRAM mode register. Memory controller code will interpret the programmed values of CAS latency, burst size as well, perform the proper operations. Delay value, how do we calculate? If you want to configure 40 ns, what you do is you divide that by 10 minus 2. That means if you program TRFC equal to 2 means you are actually programming 40 nanoseconds. That is how it works. Mean we can't configure 40 nanoseconds. You configure what? 2. That will translate to 40 ns. All these calculations are again present in the spec. Next, this talks about SSRAM. Can you read this once? All SSRAM's parameters are in respect to the clock and not configurable. Memory controller supports standard synchronous burst, pipelined SSRAMs with double cycle deselect. Take a look at this once. This talks about how read works. When you issue a read, there are some signals called as ADSC, ADB, output enable. They will decide whether you are doing a read or write. Here, you see. This means write, this means read. Please read this from the spec. Once you issue a read, after 2 clock cycles only data comes. Whereas in write, data starts immediately. So these all things you have to observe. Next is what? Asynchronous chip select devices. Write cycle and read cycle. This talks about how the asynchronous chip select device read happens. The concept of asynchronous means no clock. Means there will be pure timing values, only that will be used. So it's simple logic, you understand these signals. When you deassert a chip select means memory is being, either you are performing a read or write. Then output enable low means you are performing a read. After, once you issue this thing, after TRDV data must be valid. And once you have completed reading, you pull up chip select n and output enable. That indicates that my read is complete. Then data will go into unknown value, then it will go into floating state. Again, please read this from spec. This talks about how write happens. Same concept here. You pull down chip select n. Earlier it was output enable, now it's write enable. These two will tell that you are performing a write. You show a valid data. You hold it for TW, PW. Then you enable, bring a high, write enable. Still you hold the data for TW valid. So here write completes. Next is synchronous chip select devices. Synchronous chip select devices are synchronous to memory controller clocks. They use as ACK to indicate when they have to accept data and provide data. So simple logic is, it is same as any other memory, just that there is an acknowledgement port which will indicate whether writes or read are completed. Please read this from the specification. We were talking about TMS registers, right? For each thing there is a TMS register. This talks about those registers in detail. You see, for synchronous chip select device, these all timing variables are there: TTO, TWR, TRDZ, TRDV. For these TMS registers, these fields are there: TW, WD, asynchronous chip select devices. For SDRAMs, these variables are there. So we'll talk about these things more in the next session. In the meantime, I want you to read these things. Okay. Next, what are there? This completes. Okay. Let's understand what is dynamic bus sizing. Dynamic bus sizing is a concept where when the bus width is 8 or 16 bit, automatically 4 or 2 reads will happen. The concept where in asynchronous memories, in flash memories, if bus data width is 8 bits, automatically 4 reads or writes will happen. This concept is called as dynamic bus sizing. Next, what is memory burst cycles? Memory burst itself indicates that performing a multiple write-read locations. All bursts have to be performed to sequential addresses. Burst lengths can be, some rules are there, 16 to 4096 byte transfers. For SDRAM, this applies to both reads and writes. SSRAM, this applies only to read cycles. All devices that support burst will wrap around the burst boundaries. We'll talk about this in the next cycle, next session. If the starting address is not aligned to the burst boundary, it may wrap to around the beginning while performing a burst. That means if you are performing a start address is 2, it doesn't go to 2345, it goes to 2301. Now, how do we come up with these numbers is what we'll discuss in the next session. I want you to read this in meantime. Okay. This diagram just explains how that memory burst cycle happens. Then another feature called as read modify write. There are these few things which we will let's discuss this in the next session. These remaining aspects. So I want you to, I think whatever we are going to discuss now will be a little advanced for you. Unless you have read the memory controller's specification, you won't be able to follow these other advanced aspects. What I would suggest is take this week's time, read this specification completely, And in the next session, next week, next Saturday we'll have session. Tomorrow session, either we'll do assignments or we will not have the session. We'll cancel the session. In the next session when we meet, we'll complete the remaining topics and we'll move to the practical aspects of the memory controller environment. Do you have any questions till this point? So the next week assignment is complete memory controller specification, write 50 observations. So anyone who don't submit, probably they may not be able to attend the next session. If you don't submit, you will have to attend next batch, because we can't allow people who don't spend any time reading the things. So if you don't submit, you will have to attend in the next batch. So please ensure that you submit by Friday. What is meant by observations? Example of observation. So memory controller supports 8 chip selects. What do you understand from this one observation? What does it mean? 8 memories, 8 different types of memories can be connected. This is one observation. Like that, you write 50 observations. If you seriously sit for 2 hours, you can write all 50 observations. Just read through the spec, you'll automatically get some observations from that. So this will be serious. If I don't get any submissions, so overall batch itself will be cancelled. I mean, what does it indicate? If none of you submit any observations, the overall batch will attend. Batch will be next batch only. Overall training will be next batch only. I want you to spend time, right? Rather than just blindly attending sessions, every session without doing any homework, it won't work. You have to work on this. Only then you will be eligible for the next session. Okay. Yeah. Thank you.